All righty. Um, so welcome and thank you so much for your time and for everything that you've been working so hard on. My name is Christine Shupla. I work for the Lunar and Planetary Institute. I work with Andy Shaner. He works for me. And this is actually my home office. We're not back in our offices right now. So for this program, I'm relatively new to this program. This is the first year I've helped Andy with it because he's been doing it for so long. The goals here for this particular session, for these presentations, is for you to have an opportunity to describe what you've been learning and use those pictures to share your insights, and you're not being graded on it. Nothing that you say today is going to have an impact on the actual competition later. This is just to make sure that all of the teams get a chance to kind of get started, get practice presenting. I'll give you some feedback both on your presentation, but also in terms of little details. No matter how much we learn, and this goes for me as well, there's always things that we still have left to learn, and there's always things that that people might misconstrue or that we have common misconceptions. So there's lots of little things like that that I will give back to you. It doesn't mean that you didn't do great. So I wanted you to know all that. Does that make sense?
Yes, yeah. Thank you.
Do any of you have any questions for me before you begin?
I don't think so. No.
Okay. All right. You are welcome to start sharing your presentation whenever you are ready.
Okay, so this is our presentation about the moon.
Okay.
So we'll start off with the timeline. So 4.5 billion years ago, the moon was formed. Later on, like 0.1 billion years later, that's when they had like the solid moon. So it was like, as the core and everything, like the 3 layers, you know. And then later on is when they had like the lunar catalyst. What's it called?
Cataclysm.
I always mess that word up, but that's when that happened. And then there was like the meteoroids and asteroids that showered around the moon. Later on, the highland surfaces were much older and were made of different rocks. So yeah, that's the timeline.
Okay, so where did the moon come from? We have 3 theories. We have the capture theory, the coformation theory, and the giant impact theory. So we're gonna go through the theories about the least likely to the most likely, starting with the capture theory. So this is a theory that the moon was formed elsewhere from the Earth, and while the solar system was forming, all these celestial bodies were just going around the sun, and it was kind of like an asteroid situation where the moon came near the Earth, and it was drawn into the Earth's gravity, and that is one of the theories. So this could explain the different different composition, and it's a common occurrence, so that's why maybe we think it could have happened, but it's not, the composition isn't similar enough, so it's probably not what happened. And also, a capture moon doesn't usually follow the same elliptic of the Earth, the planet Earth. And the moon is relatively smooth and round. Capture moons aren't usually round, they're usually misshapen or oddly shaped.
So this is the coformation theory. It's also known as the condensation theory because it's saying that it all started from a solar nebula, and then that's where the Earth and the moon were both formed at the same time. So they say they have like the same, well, not the same, but similar composition as a rocky material, but the moon is less dense than the planet.
Okay, so here we have like, this is a giant impact theory, and so we have like the moon here, Earth here, and the Theia here.
So basically, you just took like a big chunk and just like combined them together.
Okay, so we're gonna go off of the giant impact theory and we're gonna explain the moon's formation from there because that's the most prevailing theory and that's the one that is scientifically agreed upon for the most part. So after the giant collision, the moon's birth was a big, traumatic, hot, messy event. So we refer to it as an ocean of magma, and it was just all these elements in the moon. And I'm going to use this prop to show you how.
I can't
the
see
moon
your camera.
formed.
Can you turn on your camera so I can see your
Oh,
prop?
our camera's on.
Oh, I thought she seen
Okay.
Okay.
So this is the prop. And so we're going to say this is the ocean of magma forming. We're going to shake it up. And so the lighter elements went to the top, which was a northocite. It's cooled liquid rock, and the heavier elements fell to the bottom, which was I think mostly iron and some nickel. This thing is not working, but the heavier elements went to the bottom and the upside down.
Shake it more. Shake it more.
And the lighter elements went to the top. So in the middle is like olivine and pyroxene and some other elements. And so that's how we understand the layers of the moon.
Okay, so this is we're gonna be talking about the geography of the moon, I mean. So we have the lunar highlands where like the lighter components rise up to the surface of the moon. Then we have the lunar mare, which are like these dark plains that are made of basalt that were made from like volcanic eruptions. And we have the impacting cratering, which is like basically they're caused by asteroids and meteoroids. And then we have the impact basins or basins, which is a large complex impact crater.
Okay, so here's more about it. So the rails were likely formed from collapsed lava tubes and volcanic domes and cones actively have been recorded in like the past 100 million years. And the breccia was likely classified debris and melt generated by bombardment of the lunar surface.
So when we're going over the lunar features, the moon has so many geographical features, and so we are just putting that into a group and saying this is the relatively common features that we see on the moon. And now we're going to take these images and we're going to say, okay, here's how the features apply to these images. So in this image, we have mostly impact craters. Well, it's all impact craters. And they're all simple impact craters, and we'll explain that in the next slide, the difference between simple and complex. But in this one, the red circles are around the older craters, and you can see that because they're not as pronounced and they're not as deep, and they kind of seem diminished a little bit, and they're harder to make out. And the newer ones, the smaller ones with the green circles around them, you can tell because they're deeper and they stand out more, and the sun is hitting them. Oh, and that's another thing we should go over. We can tell these are craters and not just volcanic domes because of the way the sun is hitting them. And so we know that the sun is from the upper left because it's hitting the inside of the craters. And it's a complicated process to be able to tell. And also, this is the Apollo 11 landing site. I wish I had something that I could point to, but in the upper right, oh yeah, okay, put the mouse there.
Yeah,
In the upper right, by the nearest red circle is where the Apollo 11 landed. And if you look really closely, there are just tiny little lines, and you can tell that those are the astronauts' footprints, and it's really cool.
Oops. So there's two different types of craters. There's a complex and a simple. The complex is more like a W shape, so it's more shallow, and there's a central peak, so you'll see it as a more W shape. And the simple is like they're usually smaller, and they're more like the U shape.
So this thingy right here is a large curve from the Hadley, and then the surrounding of it is just like lava marks and lunar dirt.
This is also the LRO mission.
Okay, so we're going to be going over reals, which is what we saw in the last image. It was a zoomed in image of the Hadley reel, and it was the landing site for the Apollo 15 mission. So reals are long depressions in the surface of the moon, and they resemble like dried out riverbeds, mostly if it's a sinuous reel. So we're going to start with the three types of reels. There's sinuous, arcuate, I hope I'm saying that right, and straight. So sinuous are very curved and kinked, and they most accurately resemble a dried riverbed, and it's thought to be formed from a collapsed lava tube or the remnants of lava flows. And then we have arcuate reels, and they're just smooth curves found on the edges of Mare. And these are just thought to be dried lava flows as well. And then we have straight reels, which they're not completely straight, but they're smoother than the sinuous reels. And so this is just a long linear path, and it's sections of the moon's crust that have been sunk between two panels, which is also in geography referred to as a graben.
Okay, so this is the Apollo 15 site. This was the 9th mission, I believe. And so right here we have the arcuate.
I think this one's a sinuous reel.
It's a sinuous.
Sinuous reel right here. And then we have like a crater, and they're both within what's it called?
Mare.
Mare, yeah. And right here, these will be the lunar highlands.
Okay, so here the Mare are like larger, darker of like art, and then the highlands are low density, and they're basically down here, and they're like they form the crust.
And there are sources. And so, yeah, that was what we learned from the packets that we went over and the research we did. And I love learning about the moon. It was a great process to go through.
Thank you all so much. I really appreciate it. Let's go ahead and, okay, so overarching big picture, smooth presentation, good confidence, good volume, good pacing. All of that was awesome. I liked the contrast on the text and the color of the photos. In some cases, the photos, just in terms of presentation style for the future, I would recommend making some of the pictures bigger and having less complete sentences, more just keywords if you want words there, because people will be tempted to read the words and stop listening to you, and we want them to listen to you. So shorter phrases rather than complete sentences and bigger pictures. But overarching, really well done and excellent pacing. And yeah, what I'd like to do now is go through your presentation from the beginning, and I'll ask you some questions, and I'll give you a little bit of feedback from each of the items as well. So great cover slide, excellent. Next slide. So for the timeline here, yeah, that crust of lighter compounds, and you've used the word later. I just want to make sure sometimes people are reading different things in different places and they don't put the pieces together. That crust, what is the type of rock that we think that crust was made out of predominantly, mostly? It begins.
I have the name of it. I just have to think. It means cooled lava. It's a hardened rock. I can't remember the scientific term for it though.
It begins with an A, and
Yeah, it does.
okay, yeah, it's not a common word. It's not a common name even for geologists. It's called a northocite, and we do have a northocite. We have a northocite here on Earth, but it's not as common as it appears to be on the Moon, and it's predominantly a particular mineral, plagioclase feldspar. And you're right. We think that it crystallized and floated up to the top. You've kind of got the order there of the magma surrounding the Moon, and the crust switched to let you know that it's this magma ocean that the materials floated up in to form the crust. So this magma that surrounded the Moon, the ocean, the magma ocean, is what forms that crust.
So these two are reversed.
Are reversed. I would switch those in your timeline. And the Moon, as it continues to cool and being smaller, which one do you think cooled first, the Moon or the Earth?
I think the Earth, because it has water, so water's kind of cool, so it'll it more.
The difference in sizes. Tell me about how big the Moon is and how big the Earth is.
The Moon is way smaller compared to the Earth.
The Moon's way smaller. The Moon's about a quarter of the Earth's diameter. So if the Earth was the size of a basketball, the Moon is about the size of a tennis ball, and you can fit 4 of them across that basketball. So if you have 2 things that are hot, let's say you're baking a cake and a cupcake, and you take them out of the oven and let them cool, which one's going to cool first?
The cupcake.
The cupcake. So the reason that we think the Moon is mostly solidified, and we don't know for sure what percentage, but we think it's mostly solidified on the inside, is because it's smaller, and so it started to cool first, whereas we know that the Earth isn't completely solidified. We know that the inner core of the Earth is under so much pressure that it's likely mostly solid, but the outer core of the Earth, we can tell from earthquake data, is liquid. The mantle is sort of solid, even though it flows, it's solid. So the Earth isn't solid completely on the inside, and we think the Moon has mostly cooled off enough that the inside, the core, and the mantle and the crust are mostly solid. So that's what that means there. So. And then the late heavy bombardment, you're right. It's also known sometimes as the lunar cataclysm, and you all were saying that. There's lots of ideas behind the formation of the lunar cataclysm. We don't need to go into intensely right now, but they're going to relate to the asteroids in the future. A lot of the research that supports this idea that the Moon received a whole lots of really big, the really enormous craters on the Moon, the one that later filled in with lava to become the Mare. A lot of them probably formed around that time or earlier. We're not sure how many of them formed earlier. There's a lot of questions there about that. But we think that that the outer planets, Jupiter and Saturn and Uranus and Neptune, there's a lot of modeling that shows that they might have formed closer to the Sun than where they are now. And as they were orbiting, their gravitational pulls were kind of tugging on each other a little bit, being closer to each other, Saturn and Jupiter in particular, and developed a resonance where they were pulling, and eventually that resonance pushed them further out. And in the process of going further out, they took a whole lot of the asteroids that were still wandering around in the solar system and threw them in.
Wow, I didn't know that.
It's called the Nice model, and it relates to this late heavy bombardment, which would have bombarded the Moon, the Earth, Venus, Mars, Mercury, with lots of asteroids at that time. And so there's these 2 different models there. Okay. And yeah, lots of basins formed, probably a lot more than 12. Some of the big ones, and some that are filled in and some that are covered up by others, because, you make a hole and then you throw an asteroid at that hole and it'll make a new hole that covers part of it up. So anyway, let's go on to the next slide. So that shower, and we're not 100% certain that it was asteroids, but a lot of scientists are leaning more towards asteroids than comets there. And then the word meteors, there's a common misconception about the use of the word meteor versus meteoroid and meteorite. I just really want to take 1 minute to clarify that. If you've got a rock in space, this size, a pebble, when it's in space, it's a meteoroid. It's too small to be an asteroid. And when it goes through Earth's atmosphere, as it's burning up, it becomes so hot, it ionizes the air and makes the air glow. And that's why we see shooting stars. That light that we see, that glow, is what we call the meteor. So the meteor isn't a rock, it's the light, the shooting star. And then when it lands on the ground, we call it a meteorite. So the shower, the moon probably wouldn't have had any meteors because there's no atmosphere, so you can't see them. Although when the moon very, very first formed, it might have had a very thin atmosphere that eventually escaped into space because it didn't have enough gravity to hold on to it. So, okay, so yes, here you're right about the highland surfaces are older. I wouldn't put a date to that. I mean, that just continues from the formation of the crust on down. So that anorthosite, from that formation of the crust, I would get rid of that particular item about highland surfaces on your timeline. That just kind of, you know, does that make sense?
Yeah.
Okay, next slide. And the moon's formation, awesome. The word theory, theory, and different scientists will spend time thinking about this, and some don't think about this at all. So some scientists really don't care about this, but people who teach the process and the nature of science do. In terms of the nature of science, the word theory generally refers to something really big, multiple phenomena, something that explains multiple phenomena. So the Big Bang Theory explains multiple phenomena, multiple things that we see. You know, the theory of plate tectonics explains lots of aspects about what we see on our planet. The theory of gravity explains lots of things. Here, when we're talking about the formation of the moon, it's one thing, sort of. So I personally would prefer, and some of our scientists as well, the ones who have thought about this, prefer the term model, or hypothesis, if you prefer, to theory for these. Capture theory. So just to let you know, and the capture model has been pretty much completely discredited. This idea about the composition, well, there's another con that kind of matches this idea about odd shapes. In order for Earth to capture something as big as the moon, you know, so you've got something the size of the moon that's whizzing by the Earth, and the Earth doesn't have, it's got a lot of gravity, but still, for us to capture it, I mean, can you imagine you are outside and there is a bull charging towards you,
Yeah.
and it's got a rope around its neck? For you to be able to grab that rope and hang on to it, that's going to be really hard. For you to grab the rope of a little dog, pretty easy. If you are a real giant of a person, you might be able to grab the rope of a bull. The moon isn't a bull. The moon isn't a little dog, though, either. The moon is a big dog. So a Rottweiler running really fast. The chances of you or I grabbing that Rottweiler and being able to hang on to it, not so good. If it's so there's and that has to do with the energy in the system, the energy of the Earth and the moon and the gravity, that energy. We're not sure if the combined energy of the Earth and moon and the speed and all of that matches the energy that would have been needed for that. And then you're right, the moon is different composition. It's a lot lighter in terms, it has a lot less iron than the Earth does percentage-wise. So the capture model would have explained that. It doesn't match. The Earth and the moon have the same ratio of certain isotopes, the same ratio of oxygen isotopes. And when we look at the ratio of oxygen isotopes for the Earth compared to Mars rocks, very different. The ratio of Earth's oxygen isotopes to asteroids, very different. So this idea that the Earth has the same ratio of oxygen isotopes as the Moon does indicates that there was some transfer of material, or there's got to be something that explains. It's almost as though, let me think of I haven't thought of an analogy for this before. Have you all, did you see a lot of the stuff about this idea about isotope composition?
I think so. There was a little bit about it.
It can get a little confusing.
Yeah.
It's okay. If you're making houses, okay? When I look out my window, the houses in my neighborhood are made out of the same sorts of things that my house is made out of. They have the same amount of bricks and the same amount of siding and the same types of roof tiles, right? And depending on where you live, your neighborhood probably has similar types of tiles for your roof, whether, whether it's adobe, certain places have adobe houses, or they have, different styles. And the people in those neighborhoods, they had the same contractor build them all at the same time, and so they're made out of the same stuff. And if you come across a house in that neighborhood that's made out of completely different stuff, it was probably created by a completely different builder. Does that make sense?
Yeah.
So, so the Earth and Moon are made out of the same stuff, same bricks and materials, but the Moon is a different model than the Earth. The Moon has a lot less iron. So I've got a 2-story house, and the house next door is a 1-story house. And so there's some things about our houses that are very, very different. The structure of their house next door to mine is very different. My house may have different windows. It might have, but same builder, same composition. So the Moon and the Earth have the same oxygen isotope ratio, and not just oxygen, others as well. But we didn't know this until we brought back moon rocks from the Moon, until the astronauts brought back moon rocks, and we were able to really analyze the composition, not just of the minerals, but of the individual molecules, and figure out what types of molecules these things are made out of. So, okay, next slide. So, yeah, capture model. Think of the bowl, trying to grab a bowl. Really hard. Really hard. The coformation model is the idea that maybe the Moon formed in orbit around the Earth, so in the same neighborhood as the Earth, which would make sense. So if it's forming in the same neighborhood, if it formed in orbit around the Earth, then it's in our same neighborhood, so that it explains the oxygen isotope ratio, because it's formed from the same materials in orbit around the Earth. It might be a little weird for that to happen, but the other issue with it is it doesn't explain, well, then why doesn't it have as much iron in its core? Why is it so light compared to the Earth? It doesn't explain. You're right. The Moon is a lot less dense than our planet, and that's the biggest issue with that one. So yeah, next slide. And the giant impact model. And there's one other model that you skipped that has some similarities with the giant impact model, and that is this idea that that the Earth was spinning so fast that some of it splattered off. And it's mostly discredited, although there's a relationship between this and the giant impact model. Let me go ahead and clarify that. So tell me a little bit, when you say that this large object, this Mars-sized object, took a chunk out of the Earth. Tell me what that's like. What happened? What?
You hand me? Will you hand me that? Okay.
So yeah, our camera wasn't showing.
Yeah, it wasn't showing.
So
yeah. Okay, so yeah, see Earth. Thank you. So this is Earth. This is our little model. And this is Theia, the green one. And so Theia came crashing into Earth. It collided, and it took out a chunk of Earth, but it didn't form together immediately. These pieces are scattered together in the solar system and space. They're just scattered. But gravity brought them together, and the theory is that they formed the moon. And then it started on the same ecliptic as Earth, and that is the theory, except we don't know. I mean, scientists, this is pretty much the theory that everyone agrees on, but there are some things still questionable about it, because the material of the moon is not similar enough to Theia. That's one of the questions they have about it. But it would explain the similar composition, and it explains the placement as well.
And often you see scientists say a Mars-sized object. Do you all know how big Mars is compared to the Earth?
Yeah,
Well, they're pretty similar, right? Like, or was that Venus?
Venus is
I
pretty
think
similar to
Mars-
Earth.
Yeah. Mars is just a little bit smaller, right?
I think Mars is like a little bit bigger than Earth. I believe.
This is one of the reasons that I really dislike that scientists use the term Mars-sized object, because that doesn't help most people, because most people don't know how big Mars is. Mars is quite a bit smaller than the Earth. Mars is only half as wide as the Earth. So, so something about half or a third the width of the Earth. And then the other thing that that there's this common misconception that this thing, just like you said, took a chunk out of it. This impact, even if it was a side swipe, Theia would have been obliterated into pieces and vaporized, and a large part of the Earth would have been obliterated as well. Think enormous explosion. Think, you know, billions of nuclear bombs all going off at once, you know, enormous explosion that would have devastated both Theia and the Earth. And so pieces of Theia, especially from Theia's core, would have fallen into the Earth and combined with the Earth's core. And pieces of the outside of the Earth and pieces of the outside of Theia would have been blown into space, forming this giant circle, this giant donut of explosion debris that was orbiting the Earth in the process. And that explosion debris gradually came together to form the moon. Does that make sense?
Yeah, it does.
And so that explosion debris, this accretion disk of material from this giant impact, as it slowly condensed to form the moon, and orbiting the Earth, and there's those two words that I hear you struggling with: ellipse and ecliptic. An ellipsis is like an oval circle, and and the ecliptic is the plane that the Earth and the other planets orbit the sun in, and a lot of people struggle with that too. So no worries there.
That's good.
So this debris gradually would have formed into the moon. And the reason that that's similar to this idea of the Earth spinning fast enough to throw off some stuff is the same material, right? You're throwing off. So the moon would have formed from what had been part of the Earth's crust and part of the Earth's mantle, as well as part of Theia. And so it explains the fact that the moon has less iron. It's less dense because it's mostly forming from the outside stuff and less of the iron. And yet you've got this exchange of material to help explain why the oxygen isotopes are similar. So it explains all of that. And in terms of the amount of energy and the energy in the Earth-Moon system and the speed at which the moon's going around the Earth and all of that, it kind of explains that. Although when the moon first formed, that accretion disk, the moon would have been closer to the Earth. We know that the moon is moving further away from us. We've measured the speed at which the moon is slowly, it's about 2 inches a year, moving away from us. The astronauts left some reflectors on the moon, and we point lasers at them and see how long it takes the laser to bounce off of the reflectors and come back to us. And that tells us exactly to precision how far it is. And it's moving about 1 inch or 2 a year away from us. And we think that back when the moon first formed, it was a lot closer. And we think that the Earth was spinning a lot faster. The Earth is slowing down in its rotation as part of this system, this gravitational system of the two of them. And so back when the moon first formed, the Earth could have been spinning, we could have had 5-hour days. And when the dinosaurs were around, our days would have been like 22 hours. And now it's 24 hours, and millions of years from now, it'll be longer, and we'll finally have enough time to get everything that we want to get done.
Yeah.
So time will stop, basically, in a way.
So, well, eventually the moon will probably escape Earth's orbit. Eventually it'll get far enough away that it'll escape our gravity. But that's not for like 1 billion years. We got time.
Okay. That's kind of scary to think about.
And so here you've got this, so as the moon coalesced out of these pieces, it was really hot at first, right? All this stuff is combining, plus more stuff is coming in from the outside, running into it. And it's really, really hot. And it differentiates, and you showed me your differentiation bottle, the heavy stuff sinking to the middle and the lighter stuff floating up to the top. And the anorthosite, lava is cooled rock. But lava is any type of rock. And here anorthosite, it's a very specific type of rock that we think is covered most of the moon's crust initially. So great job there. No changes to any of that. So let's here a lot of teams and a lot of people struggle with the terms Mare and Maria. So it's Mare, and tell me, when do you think those lava plains of basalt, when do you think they happened?
That is a really good question. Okay, so we know that, like you said, the cupcake comes out of the oven. And when you eat cupcakes, you have to let it cool first, or else you eat it and it burns you and it's kind of weird and melty, or like a brownie or something. And so that was the same with the moon. It was melty and yucky, and it was like going through puberty. It had pimples, it had volcanoes everywhere. And so a lot of these volcanoes were going off, and they formed, so you're asking about the Mare, right? So this would be in the very early stages of the formation of the moon, when it was just barely cooling off. So there would be an impact basin from, there would be like a meteorite that hit, or not a meteorite, you said?
Asteroid. Like an asteroid.
Yes, asteroid. So an asteroid would hit, and then there would be an impact basin, this huge empty space, and then it would be filled in by lava and like other lunar material. And that is how I think we understand that the Mare was formed, and that's why they're a lot darker surface, because it's less reflective than the outer crust, if that's correct.
Mm-hmm. Absolutely. So you've got the basics of it. When I first came to work at LPI, I had some misconceptions about the Mare, and so I wanted to kind of clarify them for you here a little bit as well. So you've got those asteroids making giant impact basins, and here we're talking about really big ones, right? So that impact basin not only made that complex basin with all of the tiers and everything, but it also would crack the crust. So you have deep cracks in the crust of the moon. And so later, not immediately, later, as magma pools formed within the crust of the moon or beneath the crust of the moon, as the moon continued to cool, those magma pools would find ways to go up to the surface, and they'd go up through the places that had cracks, and they'd fill it. So they filled in the low-lying areas, just like you can imagine it. They would flow out into places where it's lower, deeper craters, but also they're more likely to fill in those craters where there's cracks that they can get up into them. So, so a lot of the Mare probably happened around 3 billion years ago. Whereas the basins themselves, many of those you already said probably formed, a lot of them formed around 3.8 billion years ago. But the lava flowing up, we're thinking 3 billion years, and some pieces it might have been as recent as 1 billion years ago.
Yeah.
Okay.
That makes sense. Thank you.
All right.
Anything else on that slide?
Nothing else on that slide.
Okay.
Everything else there is good. Next slide.
So for future presentation, do you think we should just like add pictures and then describe what they are, or?
Yeah, and generally in terms of presentation styles, yes, pictures are good. You know what you're going to say. You want people looking at you and less focused on reading sentences. So yeah, use some pictures are good, or just fewer words. So that way, I mean, I don't mind reading the words, and it's nice. But in terms of presentations, fewer words, more pictures demonstrating the thing that you are trying to show. And for instance, you know, the differentiation bottle, you could have taken a picture of it, a couple pictures of that, and put that in there.
Oh yeah.
Or you could have taken pictures of the balls or things like that. It doesn't have to be just the science pictures. The presentation that you're going to do in the spring is really going to be about your research. It's not going to be so much broad descriptions like this anyway, but still, yeah, pictures are good. Rills here, you went later through the 3 different types of rills, no changes there. Volcanic domes and cones. The Mare tend to be pretty flat and smooth, as you've said, but they do have places where there's some volcanic domes and cones here and there. I don't, the activity in the last 100 million years, that might be, that I'm not confident about that, but I believe you. If you saw research saying that, I believe you, but we'd be talking really, really little bits of activity. Probably from LRO is probably where you found that, as my guess. The evidence, and it's not that we've been able to date it exactly. Those dates would be estimated. Do you know how do we estimate dates of when things happened on the moon? What are some ways that we can estimate?
Don't we use carbon dating?
Not carbon, because carbon works for like thousands of years. It doesn't work really well for millions or billions. But we can use something similar to carbon dating, but using things like potassium and thorium if we have rock samples. But for most of the moon, we don't, right? We only have rock samples from when the astronauts brought things back, and then we have meteorites from the moon. We know that they came from the moon because of the composition, but we don't know which spot on the moon they came from. So for most of the moon, we date based on the number of craters. If you've got a lot of craters, then it's been sitting there exposed and getting hit for billions of years. If there's fewer craters, that tells you that something covered up the older craters. So the Mare, we can date how recent certain parts of the Mare are based on how few craters are there. There'll still be some craters because there's constantly things still hitting the moon, you know, and the Earth and every place else, but not as many as there used to be.
Yeah.
Okay. Breccia, I wanted to clarify here for you. Breccia isn't really a geographic feature. Breccia is a type of rock. And that type of rock makes up most of the moon's surface. When we said anorthosite, even here at NASA, they've got a lot of the moon rocks that they found on the moon, and they tried finding like the best anorthosites that they could. They were looking for some specifically. But most of the rocks are actually, instead of just, you know, if I go outside and I can, you know, pick up a sandstone, you might, there in Utah, probably pick up a sandstone that's formed from little pieces of sand that have been glued together over time into a rock. The moon has little pieces of moon rock that have been glued together over time, but what broke them apart in the first place was impacts. The moon's surface has been hit and hit and hit and hit and hit and broken into pieces from big asteroids and from little asteroids and from little meteorites all over the place. And so think of it just constantly getting pulverized and those rocks getting cemented together from the heat and pressure of other impacts. And so yeah, most of the rocks on the moon are made of pieces of other rocks rather than like a piece of lava that is cooled. Or like a piece of anorthosite that formed from the initial crust. Most of them are pretty smacked up. And so breccia is just the type of rock. Think of it, a breccia, as being like a conglomerate, except in this case, it's a conglomerate specifically of pieces that have been glued together on the moon from impacts more than anything else.
That makes sense. Thank you.
Okay. All right. I believe that this is Apollo 12 and not Apollo 11. You're right about the footprints, and the footprints also, there's a place where they're dragging along a case or like a roller behind them to help them collect things. You're right about the craters that are less well defined. Over time, with all that stuff going on, they kind of get a little, a little less sharp. And the sharper craters tend to be younger. The craters that have more craters in them are older. Like I said, you can tell how old an area is by the number of impact craters. So the more craters you have in a circle, the older it is compared to the ones that have fewer craters in that area. Does that make sense?
Yeah, it does.
You're looking at all those red circles and seeing how many little holes are in them compared to the number of little holes in some of the green ones maybe. And then one other feature for young craters versus older craters, younger craters, the really, really, really young ones, tend to be brighter, tend to be whiter. The material that gets flung out, all of that is whiter. Over time, particles from the sun interact with the rocks on the moon, and it gets darker. So over time, older areas get darker, and so fresh craters tend to be brighter. So,
okay. Thank you.
Awesome. Next slide. I know we need to get on to the asteroid one. Sorry. No changes here. It all looks great. You're right, this is Apollo 15, and that is Hadley Rill. Two things I wanted to, the bright area, bottom center, do you see where it's kind of bright there?
Yeah, we do.
Any ideas why that might be brighter?
I wouldn't know.
I wouldn't have either, but I've listened to a lot of Andy's presentations in the past on this. When we go to one of the other features, let's skip ahead two slides here. That one. Do you see where the first picture was part of this one? Can you point, do you have any idea where it was?
Like right here, either there or up here.
It's some part of it. We're not exactly sure where, but we know it's part of it.
You know it's part of it. Go a little bit further up to the right, just a little bit on the rill though. Do you see that? Yeah, right there. And then down just a tiny bit closer to the highlands, right there, that curve where it turns, that curve where it's going from here to here, that's it. And do you see how the highlands are right next to it?
Yeah.
So Andy, I heard Andy suggest, and do you see that there's a crater right there on the highlands?
Yeah.
Oh yeah, right here.
So that crater, that impact probably splattered highland materials, which as you mentioned is lighter in color, down there. And that's probably some rocks from the highlands that got splattered down, making that lighter in color. So
that makes sense.
Yeah, that would make sense.
While we're here, so you've talked about the highlands and pointed them out. You've talked about the Mare. You've talked about the sinuous rill. It's not an arcuate rill. It's a sinuous rill. And there's a big crater there. Can you tell me the order? What came first and what came last of those four things? The highlands, the Mare, the rill, and the crater. Which thing do you think came first and which thing do you think came last? And do you have any ideas why?
We can't tell you the order. So
the Mare came first.
Yeah, the Mare came first.
Then was the sinuous rill, and then the crater, and then the lunar highlands.
I think my theory would be that it was the Mare and then the highlands and then the sinuous rill and then the impact crater. You can tell the impact crater was last because it just by the layering of it, you can tell that the reel doesn't go through the crater.
Right. So you can tell, so you have to have the Mare before the rill, right? Because you can't form the rill on top of the Mare unless the Mare is there.
Mm-hmm.
And you're right, the crater formed last because it's on top of the rill. The Highlands was first.
First?
The Highlands is first. You can see where the lava from the Mare went in around the edges of the Highlands, filled in those flows.
Adams, come to the office, please. Mackenzie Adams.
That process is called embayment, and it filled in things there. So, so the Mare came last. The Highlands were first, and the Mare came second.
That makes sense.
So think of the Highlands as being part of that original crust and getting hit, and so making those big basins, and the edges of the mountains are probably from a previous basin that was there. And yeah, okay, good job. Let's go back to the middle slide. And we're almost done, I promise. Okay, rills, that all looked, everything else there is fine. The rills, your talk about the rills is great. I wanted to add just one thing. The straight rills are associated with a type of tectonics on the moon. Our moon over time shrunk as it cooled off a little bit, and so cracks formed in the crust where, those straight rills, the graben, are related to the crust kind of getting crinkly as it shrunk. Like if you take a balloon and you inflate it and then you stick it in the freezer, as it starts to cool, it'll shrink, and as it shrinks, the edges of the balloon will kind of get all wrinkled. That kind of happened to our moon. No, yeah, keep going. And then that last picture of the moon, let's take a quick look at that.
Will the following students come to the office, please?
I know.
Cornelius, Connor
I
Hunt, Raquel Forbush, Tyson Memmott, Jennifer Trujillo, Aspen Chapel,
So which image we have? This is just an
Brayden
example.
Carter, Parker Bryan, Morgan Black.
I like this image here. The Highlands there is all the brighter areas, and the Mare are all the darker areas. And Mare is plural, so that's great. No other changes here. How much time do you have left? Because I know you still have your asteroid one, but I know it'll be shorter probably. How much time do you have left right now?
Okay.
We didn't.
So we actually decided, just because of time and because they're seniors and their focus was the moon, that they were just going to stick with the moon for this year.
Okay.
As exciting as asteroids was, and Bennu and everything that's been happening, but we just decided time-wise we would stick with the moon.
Okay, cool. Do you have any questions for me?
Nope. We're super thankful that you were willing to take time out of your day and help us out and go over some things. That was really helpful. We'll use it in the future.
Thank you.
Thank you.
You're very welcome, and I am certain that your mentor will be able to explain in lots more detail as well if you have any other questions, but I'm happy to help. So thank you all, ladies, for your time. Great presentation, and look forward to seeing more.
Thank you.
Thank you very much.
Thank you.
All right, bye-bye.